Episode 6 Carbon Black, Jetness, UV Absorption, and Rheology Control in Automotive Coatings. In this episode, we focus on carbon black, one of the most widely used pigments in automotive coatings, particularly for primers, solid black topcoats, and functional layers. While it may appear simple at first glance, carbon black has complex optical, chemical, and rheological behavior that makes it a critical pigment in coating design. Understanding carbon black requires examining its optical properties, particle morphology, surface chemistry, interaction with binders, and influence on application and durability. Carbon black is primarily a form of elemental carbon produced by controlled incomplete combustion or thermal decomposition of hydrocarbons. Unlike organic pigments, which derive color from molecular absorption, or inorganic pigments, which rely on metal-based structures, carbon black is an almost pure light-absorbing material. It absorbs visible light across nearly the entire spectrum, which results in its deep black color and high jetness. Jetness refers to the depth and purity of blackness perceived by the human eye, and in automotive coatings, achieving maximum jetness is a key quality parameter, particularly in high-gloss black topcoats. The optical behavior of carbon black is heavily influenced by particle size, structure, and aggregation. Primary particles are extremely small, typically in the range of 10 to 50 nanometers. These primary particles form aggregates and agglomerates, which are larger clusters held together by van der Waals forces. The structure of these aggregates, described as branching or chain-like, affects light absorption and scattering. Aggregates with higher structure contain more interparticle voids, which can influence color intensity, transparency, and dispersion behavior. Low-structure carbon black provides deeper, denser black color, while high-structure grades offer better coverage and flow but may reduce jetness. Surface chemistry is another critical factor. Raw carbon black particles have a large surface area and are highly reactive due to edge carbon atoms and functional groups such as carboxyl, hydroxyl, and quinone. These surface groups can interact with binders, dispersants, and additives, affecting wetting, dispersion stability, and rheology. Automotive-grade carbon blacks are often surface-treated or functionalized to improve compatibility with specific resin systems, reduce flocculation, and prevent undesired interactions with curing agents. Dispersion of carbon black is challenging due to its strong tendency to form agglomerates. Achieving a uniform dispersion requires sufficient mechanical energy, proper wetting agents, and sometimes specialized dispersants. Poorly dispersed carbon black results in streaking, color inconsistency, reduced jetness, and higher haze in the coating. Proper dispersion also ensures that the pigment fully contributes to both color intensity and UV protection. Carbon black has a unique role in UV absorption. Unlike other pigments, it effectively absorbs ultraviolet radiation, protecting underlying layers from photodegradation. This is particularly important in multi-layer automotive systems, where primers, fillers, and base coats need protection from sunlight to prevent chalking, fading, and loss of mechanical properties. The UV protection offered by carbon black depends on particle size and concentration, as these determine the overall optical density and the depth to which UV light can penetrate. Particle size also affects viscosity and rheology. Due to the extremely high surface area of carbon black, it significantly increases the viscosity of coatings, even at low pigment loadings. Aggregated carbon black can form a three-dimensional network in the binder, imparting yield stress and affecting flow and leveling. High structure grades tend to increase viscosity and provide thixotropic behavior, which is useful for preventing sag during vertical applications, but can make spray atomization more challenging. Formulators must carefully select the grade and loading of carbon black to balance jetness, coverage, UV protection, and application properties. Density is another practical consideration. Carbon black has a relatively low density compared to inorganic pigments, meaning that volume-based calculations are critical in formulation. This affects pigment volume concentration, CPVC considerations, and overall film properties. Because of its low density, carbon black contributes more effectively to optical density per unit weight, but may still require careful dispersion to prevent settling and storage. Carbon black is chemically inert, making it highly resistant to acids, alkalis, solvents, and oxidative stress. This chemical stability contributes to the durability of automotive coatings. However, it is not entirely passive. Its interaction with other pigments, particularly titanium dioxide and organic pigments, must be considered to avoid flocculation, color shifts, or rheological issues. In black and gray formulations, carbon black is often combined with titanium dioxide or extenders to optimize hiding, viscosity, and cost, while maintaining deep black color. Another key role of carbon black is in influencing mechanical properties. The rigid, high surface area particles reinforce the cured polymer network, improving hardness and scratch resistance in some coating systems. However, excessive loading or poor dispersion can lead to stress concentration points, microcracking, or loss of gloss. This is why carbon black loadings are carefully optimized for both functional and visual performance. From a formulation standpoint, carbon black is often added in small but critical quantities. Even a slight change in particle size distribution, surface treatment, or dispersion energy can alter jetness, gloss, and application behavior. In multilayer automotive systems, carbon black is frequently used in primers, fillers, and base coats to provide opacity, UV protection, and background support for subsequent layers. Its role is both optical and functional, rather than purely decorative. Carbon black also interacts with effect pigments in metallic and pearlescent systems. Its strong light-absorbing properties can enhance contrast and visual depth, making metallic effects appear brighter against a darker background. Careful selection and blending are essential to avoid undesirable darkening or dulling of effect layers. In summary, carbon black is a multifunctional pigment that contributes jetness, UV protection, rheological control, and mechanical reinforcement in automotive coatings. Its performance depends on particle size, structure, surface chemistry, dispersion quality, and interaction with binders and other pigments. Mastery of carbon black selection and handling is essential for achieving high-quality black and dark-colored automotive finishes that meet both aesthetic and functional requirements. If you have any questions about carbon black, its grades, dispersion, UV protection, or its role in automotive coatings, leave them in the comments and I will clarify them in detail.